All right, this is Chapter 4, Review Worksheet number 1. Let's look at the first free response question here. It says a particle moves along the y-axis with velocity given by v of t is equal to t sine of t squared for t is greater than 0. In which direction is the particle moving at time t is equal to 1.5? So first off, we're going to have to use a calculator to plug this in. Make sure that your calculator is in radian mode. It's always going to be in radian mode, so it should never be in degree mode. So part A is simply asking you to find or evaluate the velocity at 1.5. Okay, so in your calculator, you can plug in this function. You can simply go into y equals, plug in x sine of x squared, since the variable in the calculator is x. And then you can go to vars, y vars, function, y sub 1, and then simply plug in 1.5. So all this is doing is you're telling the calculator to evaluate this function at 1.5, and you're going to get 1.167. We're going to round to 3 decimal places. So the velocity at 1.5 is 1.167. And because the velocity is greater than 0, we know that this particle is going to be moving up. So the two directions that we can be moving in is either up or down. Up will be positive, down will be negative. And this doesn't indicate any units of measurement, so we just leave it like this. Okay, if it's meters per second, then we would have to indicate that. Okay, so here's our reasoning. Positive velocity, so particle is therefore moving up. Okay, part B, find the acceleration of the particle at time t equals to 1.5. Now acceleration is simply the rate of change of velocity, or in other words, acceleration is the derivative of velocity. So the calculator can allow us to evaluate the derivative at a specific value. So if we plug in the calculator this y sub 1, this velocity function, then we can use this this function in the calculator, the n deriv, which you can go to math 8 n deriv, and here we plug in the expression. The y sub 1 will represent the velocity, our variable, which is x, and then the value that we want to evaluate the derivative at, which is 1.5. So plug that in, and in your calculator you should get negative 2.049. So this tells us that the acceleration at 1.5, at times 1.5, is going to be negative 2.049, and we know that the velocity is therefore decreasing, right? Because acceleration is simply the rate of change of velocity. Negative acceleration means we have decreasing velocity. Okay, part C, given that y of t is the position of the particle at time t, and that y of 0 is equal to 3, find y of 2. So if I want to find the position at a specific moment in time, they will always give you your starting position. So my starting position is at y sub 0, which is 3. And so I'm starting at y sub 0, and I also need to find out the distance that I traveled from the 0 to the second, from t equals 0 to t equals 2. So that's what this represents. Okay? The definite integral of my velocity function from 0 to 2 would indicate the distance that I traveled. So I add this, or displacement, I add this to my initial position, and that will give me my final position. So to plug this in your calculator, you're going to go to math 9, which we'll call the fn integral, and the arguments is, first off, you have the expression y sub 1, just like before, the velocity function. X is the variable, and then you're going to start with the lower bound and then go to the upper bound. So plug that in. So between 0 and 2, this particle will travel 0.827, so we add that to our starting point. So 3 plus 0.827. After 2 seconds, this particle, or after, let's say, t is equal to 2, the particle will be at position 3.827. Okay, part D, find the total distance traveled. So this is simply in the calculator. Just plug in the same information, but now instead of just y sub 1, you're going to call the absolute value. So ABS of y sub 1, that will ensure that every y value is converted to positives, and we get the total distance. All right, number 2, the temperature in degrees Celsius of the water is in the pond is a differentiable function, W of time t. So the period shows the water temperature is recorded every 3 days over a 15-day period. Okay, so we have 2 columns here. The first column represents the days, and you see that each of these time intervals are evenly spaced, and this next column represents the temperature at these specific these specific days. Okay, so part A, use the data from the table to find the approximation for W prime of 12. Show computation that leads to your answer. Now, W prime of 12 is simply asking us to find the rate of change, or the rate of change of temperature at the 12th day. Okay, so rate of change is simply slope. So if I find the slope on the 12th day, okay, and because we have multiple values here, the best we can do is find an approximation. So we just pick 2 order pairs around 12. So 12, 22, and 15, 21 will work. But some of these answers may be a little bit different depending on which order pairs that you choose. But I chose the order pair 12, 22, and 15, 21. Simply find the slope, and this will give us an approximation as best as what the values given us to us in the table will provide. So the rate of change of temperature on the 12th day is approximated with the value -1 over 3 Celsius per day. So the rate of change is -1/3 degrees Celsius. Okay, part B. Approximate the average temperature in degrees Celsius over the time between 0 and 15 days using a trapezoidal approximation. So first, approximating the average temperature, we have to use the average value theorem, which is 1 over b minus a, the depth integral from a to b of wt dt. So we just plug everything in as we see it. But here, the best we can do here is find an approximation. We're going to use the trapezoidal approximation. And the trapezoidal rule, we can use trapezoidal rule because each of these t values are evenly spaced. So rather than finding the individual area of each trapezoid, we can condense it into one formula here. So the width over 2 times all the heights added together. So my width is represented by my number of days. So each of the interval is 3 days, so 3 over 2. And then I'm just going to go through and add up all the quote-unquote heights, y values. And I'm going to use each of the y values twice, except for the ones at the ends. Those are the ones that are not shared between between 2 trapezoids. So we find the area using trapezoid approximation, and all that's going to give us 376.5. So 376.5 times 1 over 15 is 25.1 degrees Celsius. So you can think of this as area divided by the width gives us height. Okay, part C, a student proposes the function P given by P of t as a model for the temperature of the water at any moment in time. Find P prime of 12. So now we have a function, so we can find the exact rate of change on the 12th day. So we plug this in for y sub 1, and again we use nderiv in the calculator to evaluate the derivative on the 12th day. So plug that in, you're going to get -0.549 degrees Celsius per day. Okay. make sure you have your unit of measurement. There's a rate of change in temperature on the 12th day. Hey, use the function p in part C to find the average value over the time interval between 0 and 15 days. So again, find the average value. So go through the formula, 1 over b minus a, definite integral from a to b of p of t dt. So we plug this in the calculator using fn integral y sub 1 comma x comma 0 comma 15, and that'll give us 386.362 divided by 15, which is 25.757 degrees Celsius will be the average temperature over the course of those 15 days.